Good morning, everybody. I hope you're all okay. Apologies for Tuesday, for the webinar not being done on Tuesday, but I'm afraid we've had quite a bit of sickness in the UK with colds and flu, etc. Well, we're ready to go today anyway. So what we're going to be talking about today is understanding of electrostatic hazards. The objectives of the webinar are to look at how static charge can be generated, and more importantly, how it accumulates in a manufacturing facility. We'll also consider the different types of electrostatic discharge and their relevance to an electrostatic hazard assessment. We look at the ways to control electrostatic charge generation, and as I said, more importantly as well, the accumulation of the charge and how it can be ignited. And having an understanding of this, then we can find out how to reduce the risk. To start with, a little bit of background about Sigma-HSE, in case you haven't heard of us or you've heard about us but know little about us. We have technical offices in Winchester in the south of England in the UK, in New Delhi in India, in Mumbai in India, in Hyderabad in India, and New Brunswick in the USA, New Jersey. We have testing laboratories, our main one being based in our headquarters in Winchester, UK, our process safety laboratory there. And we have another process safety lab, which we've moved from Delhi to Hyderabad in India now. So it's a brand new testing facility. The areas of expertise that we bring are combining our Indian and UK experts to provide our clients with EHS services and appropriate engineering solutions. So the idea is not really just to come on site, do a check on your facilities and give you a report. He's trying to find out solutions to your problem and work with you to try and resolve the issues so things get to a safe level. We undertake laboratory testing in our UK laboratories, and we can follow ISO, BSI, and ASTM standards. So we cover worldwide standards in general, including the EN standards, which we'll quote within the BSI system. We look at consultancy, where we can either do desktop assessments for you, we do testing, and we do training. Today is a normal type of training that we do over the internet for people where we can't easily go and visit them. The consultancy service we provide, and this is a range of it, is a specialist technical knowledge. We cover process safety management, the implementation of it, how do you start off putting it together, combining it, and finally review of it. DESIR, which is the Dangerous Substances, Explosive Atmospheres Regulations in the UK, which are a combination of the ATEX directives and the Chemical Agents Directive, and in the UK they've combined those together to form DESIR. The rest of Europe tends to look at ATEX and Chemical Agents Directive as two separate standards and ways of looking at it. We can help you with hazard identification and hazard operability studies. So someone can come on site and deal a hazard with you, and they can lead it or they can scribe. This is the best way to do it, is to have someone in a hazard who's not involved in the system in an everyday basis. And basically, the simple process is you can ask silly questions that someone who's involved with it all the time may not ask. And therefore, you'll be surprised at some of the answers you get when you ask these silly questions. We can do process hazard analysis, the PHAs. We can look at functional safety, safety integrated levels under SIL. Chemical reaction hazards. We have a test lab in the UK which can look at chemical reaction hazards, and we have technical ability to help you with those problems. And then we do training workshops, in-house ones where we come to site and we help you with specific subjects, or a general training course looking at process safety, or we do things remotely like we're doing now. The laboratory testing covers a few areas, especially in our UK operation. In our UK, we look at powder, fire, and explosion properties. So this would be ignition sensitivity, fire properties, explosion severity, etc. And in our Indian lab, we can look at the ignition properties, how sensitive materials are to ignition. The UK lab can look at gas and vapor properties as well, such as flashpoint, AIT, LEL, etc. We also have an electrostatic properties test laboratory, which looks at things like powder volume resistivity, charge relaxation time, chargeability. We can look at measuring plastics, shoes, and that type of thing for you. And then there's chemical reaction hazards testing, where we have such things as DSC, our Carious tube, ASST in our laboratory in the UK. Shortly, we're hoping to increase our capabilities in the Indian laboratory, in India, in Hyderabad, with CRH testing as well. So, why electrostatics? Well, obviously, the word sometimes makes people think it's a bit of a black art, it's something we don't quite understand, or they confuse it with electrical problems and they give it to the electrician to look at, which sometimes seems to work okay, but in a lot of cases it doesn't, because they don't understand the differences between electrostatics and electrical problems. It's one of 13 potential ignition sources given in 1127, EN 1127. And more importantly, it's the only one specifically mentioned to be assessed in the ATEX directives. It's not very well understood and often confused with electrical measurements. It's too complicated, people say. It's a dark art. It's often blamed as an ignition source when it's not the reason for the ignition, because people don't thoroughly understand it. They don't understand the types of discharge or how things generate and accumulate charge. The most interesting thing in a manufacturing environment, it's ever present. It's inherent in the majority of processes. So once you start up the machines, etc., or people start walking around, you get movement and you get electrostatic charge generation occurring. It's the cause of a number of industrial incidents, some of them quite big. So therefore, this is one of the reasons it's been specifically mentioned in ATEX, because it is something you can deal with. Let's look at a couple of incidents here. We had the Barton Solvents explosion in July 2007. They had a flammable liquid storage tank farm, and the explosion occurred, and the static discharge ignited ethyl acetate vapors. The complete tank farm was destroyed, and nearby communities had pieces of tank farm embedded in their walls, on their roofs, and in their gardens. They had to evacuate the nearby communities as the fire intensity grew and the explosions grew in intensity. The strange thing about this one was that they thought they had done everything right. They thought they'd grounded everything, but they hadn't. They failed to identify an isolated conductor in the float. And it was this that built up static charge, discharge, and ignited the ethyl acetate vapors. So even when you think sometimes you're doing the right things, you can miss something if you're not well au fait with electrostatics, and then you get the spark. ExxonMobil explosion, February 2015. This happened in, of all places, an electrostatic precipitator. In this case, we knew you were going to get sparks because it's an electrostatic precipitator. So you knew there's going to be continuous sparks available at all times. The idea here was to prevent any flammable vapor entering this area. But they failed to do that. They failed to identify how hydrocarbon vapor could enter into the ESP. And once it did, the inevitable happened. The continuous sparks were of sufficient strength to ignite the atmosphere. This caused on-site property damage and injuries to operators. The Caswell Adhesives fire in May 2007. Ignition of flammable vapors due to static discharge. Fire destroyed the building. More than 60 firefighters were required to tackle the flames. 35 firefighters and 2 people were treated in hospital after breathing chemical fumes and smoke. One of the problems that we find when working with adhesives are a lot of them are insulating. They're very insular in nature, and they often cover the floors, they cover the equipment, and it results in isolated people and equipment. And this can often result in a static discharge. I'm not sure what happened in this one, but I would assume from experience that this is probably the cause of it. If you want to read up a little bit more and you're bored at night and you want some reading, then you can read BSEN 6079 32-1 2015. This is the Electrostatic Bible in the EU. It looks at explosive atmospheres, electrostatic hazards guidelines, and it will tell you everything you want to know about electrostatics, how to deal with them. But always remember, even though you've read it, a little bit of knowledge is a very dangerous thing. If you work in America or work with American regulations, then you've got the NFPA 77 from 2014, recommended practice on static electricity. So the types of equipment here is an illustration where the higher risk of ignition being happening. And you can see statics there, mechanical and smoldering. And if you look at A, silos and bunkers, you look at E, dryers, they're quite areas where you can get electrostatic problems for ignition. And others of them are dust collectors, which are quite a common area, conveying areas, and you can get mixing and sieving, which can cause problems again with electrostatic discharges igniting a flammable atmosphere. So understanding static electricity. What is it? Well, static electricity is generated, as I said previously, wherever movement takes place. Here's the man walking along, quite happily minding his own business. He comes up to the door, goes to touch the door handle, and he sparks to it. You know yourself, everyone's experienced it. You get out of the car, go to close the door, and you get an electrical shock from static charge buildup. So why do you get this shock? The main reason is the charge potential difference that you have. If you look at the man walking, then he's walking along on insulated shoes, on insulated lino or carpet, and then he comes to an earth door. So in all that time, he's had no way that he could discharge the static that's building up on him. So he's generating the charge, accumulating it. The only way he can get rid of it is with a spark discharge to the door handle. In the car, you're moving in the car, your clothing rubs against the seat, and all the time you're generating electrostatic charge. When you get out of the car, you don't touch earth as you leave. You just push the door open, get out, and then push on the glass maybe or on the metal door to close it. Because car companies and the tire companies in particular spend millions making anti-static tires, the car dissipates its charge very quickly. You still have your charge because you've got insulated shoes on. You touch the metal of the car and you spark. So it's not the car sparking to you, it's you sparking to the car. So static electricity is defined as an imbalance, surplus or deficit of electric charge within or on the surface of a material. The phenomenon of static electricity requires a separation between positive and negative charges. And this will occur, I'll talk about that later. But it's this separation of positive and negative charges. Static electricity is the same as mains electricity. It obeys the similar laws, but static electricity is generated in a different way. Mains electricity is a constant voltage system. As you know, in America it's 120 volts. In the UK it's 220, 240, as a lot of Europe is. But static electricity is a constant current system. So in a constant voltage system, the ampage changes. In a constant current system, the voltage can change. It's not all bad with static. Sometimes we use it for good. Sometimes it becomes an excellent way of working. If you look at photocopiers, they use electrostatics to provide the photocopy. Car spraying, for instance, you can use electrostatics to give you an even covering and coating. If you look at static precipitators there, again, they're using electrostatics in a very useful way. The same with the printer, they're there. If you look at powder coating, which is getting very popular within the car industry, then again, to put the powder onto the metal object, they use electrostatics to do that, to give you an even coating again. But now we come about the problems with electrostatics. These are the ones you normally hear about. You very rarely hear the good things. Normally you only hear the bad things. So shocks, nuisance. If you have electrostatic charge and someone gets a shock, it's not just the fact of the shock. It's the fact is they can make you jump backwards. And in some instances, people have even gone over railings because they've had a large shock and gone back so fast, they've gone over the safety barrier. Nuisance. You don't want to have to keep walking around getting electrostatic shocks. If you're in a shop and you're shopping and all the time you touch something, some conductor, you get a shock, you don't go in that shop very often. You get clinging powder attraction. So the powder sticks together, won't break up in lumps, which makes it very difficult to pour. And powder segregation. If you see the pictures below, you've got a mixing on the left, then the start of segregation, and then the final one is total segregation. In the pharmaceutical industry in particular, this can be critical when you've got milligrams of active pharmaceutical ingredient in there and it separates out. The worst case scenario, a large spark capable of igniting a flammable atmosphere, and you're in an EX rated zone, or you have that flammable atmosphere present. So now you've got the risk of an explosion occurring here. So you've either got to get rid of the flammable atmosphere, or prevent the spark, or end up having to inert the atmosphere with nitrogen. Here's the worst case scenario. We've got a flammable atmosphere occurred, and we had an electrostatic spark, and that's the result. And often that just doesn't stay with one vessel. By the time you've ruptured one, it goes on to the next, or a pipe gets broken off and it goes on to the next and the next. And then you lose half or even all of your plant. So let's look at some definitions. We have conductive. This is materials with a low electrical resistance. In other words, the electrons flow easily across the surface or through the bulk of these materials. Charges go to ground or to another conductive object that the material contacts or comes close to. So the charge is dissipated instantly. They possess a conductivity greater than 10 to the 4 picosiemens per meter. But normally we measure for powders in ohm per meter, and this will probably be about 10 to the 3 ohm meters. Anti-static, static dissipative. For these material, the charges flow to ground more slowly in a controlled manner, and then the conductive materials. Charge generation rate is less than the charge relaxation rate. In other words, you get rid of the charge faster than you can build it up. And this is how your shoes work, your floor, etc. It's static dissipative rather than conductive. If you had a conductive floor and conductive shoes and you got static blown through, you could get a very bad shock with it. So having it controlled in its release is better in those types of instances. Non-conductive, insulating. These materials prevent or limit the flow of electrons along their surface or through their volume. There are two ways to dissipate the charge. There's either through the material or along its surface. They have a high electrical resistance and you cannot ground them. So even if you connect an earth to them, you can't ground them because they cannot transfer the flow of electrons across their surface or through them. Static charges remain in place on these materials for a very long time. Charge generation in this case is greater than charge relaxation. An interesting point, and one of the worst I've seen, was an active pharmaceutical ingredient we placed in a stainless steel container, which was earthed, and left it for 28 days, and no charge was left. It had the same charge at the end of 28 days. Nearly impossible to work with, this one. Then we have static electrical discharges. So this is release of static electricity in form of either a spark, which is the most common one, brush discharges, propagating brush, cone, or corona discharges that might be capable of causing ignition under appropriate conditions. So how are we going to do our static hazard assessment? Well, it's broken down into several units. Firstly, do we have a flammable atmosphere? So if you work above the UEL or below the LEL of a liquid, you may not have a flammable atmosphere. But if you work within the flammable range, you will have. Powders, near enough impossible to stay out of the flammable range unless you can manage to keep it below the MEC, the minimum explosive concentration, but they're not homogeneous, so they tend to send slugs of powder through a system which is within the flammable range. Do we have charge generation? We know charge happens with movement, so we've got the potential for charge generation. Charge accumulation now. Can we accumulate that charge? Is it isolated where we're working? So is it an insulator? Do we know the material's ignition sensitivity? What's its minimum ignition energy? Is it very low, 3 millijoules, 1 millijoule, or is it high, up to a joule? This will decide again which route you take. And what type of discharge can you get? Can you get a corona, a cone, a brush, a propagating brush, a spark? So if we've got a flammable atmosphere for gases and vapors, we need to know the flash point. What temperature can the material ignite? Limiting oxygen concentration, just in case we need to inert. The liquid conductivity, is it an insulating liquid or a conducting liquid? The gas group of it, is it 2A, 2B, or worse, 2C, such as hydrogen? What's its flammable concentration, lower explosion limit and upper explosion limit? And with vapor density, does the material fall or rise? If it falls, you've got a problem along the ground. If it rises, then you've got a problem in the roof space. And the minimum ignition energy, as I said, again, normally for gases and vapors, this is below 1 millijoule. Similar approach occurs for dusts. Particle size. Is it below 500 micron? If it is, then you've got potential for a flammable atmosphere. Limiting oxygen concentration again. Minimum explosive concentration. Are you working below it? As I said, beware here, because dusts are not homogeneous like gases and vapors. Do you know the powder volume resistivity of it? Is it insulating, conducting? And how long does the charge remain on it? Is it 28 days like the active pharmaceutical ingredient, or is it less than a second? And the minimum ignition energy, is it down below 3 or 1 millijoule, or is it up to a joule? So we know charge gets generated with movement. A couple of pictures on the right-hand side there. You've got a man pouring probably insulating material out of a bag. You've got the flow of material through a pipe. Again, you've got separation here, negative and positive. It's much worse with insulating type materials. Insulating shoes, walking on an insulating surface. Rollers with, say, acetate sheet going around them. Spraying, a very high intense area. And then you've got inside some form of cyclone or something like that. Again, you see charge separation, positive on the equipment, negative on the powder. So the most common charging mechanism is contact or tribocharging. This is the most common you get, where something contacts together, or they're different parts of the triboelectric series, where further away they are on this series, the more risk you have of charge generation occurring. At least one of the materials must be non-conducting or insulating, such as the shoes with walking, the liquid through the pipe. Other mechanisms you get are charge sharing and induction charging, but you only can have induction charging for insulators, only for conductors with induction charging. So contact charging examples, we have a tank farm, we have a reactor coming out to a centrifuge, a vacuum dryer, in a mill before bagging. So looking at the liquid side, we have a liquid transfer through hoses and pipes, agitation here in the reactor of a two-phase mixture, settling of the two-phase mixture through the centrifuge and the vacuum dryer, filtration through the coming down there into the before you bag it. In the powder handling, you've got sieving, pouring, mixing again, milling at the end, and pneumatic transfer. All these are areas where you have high agitation and high movement of materials. If we look at induction or ionic charging, let's have a look at two metal spheres sitting on an insulating base. We then apply a charge to them. And you can see in diagram 2 the presence of a negative charge induces E to move from A to B. In other words, the two systems are now polarized. So sphere A is ending up being positive, and the furthest one ends up being negative. You carry on charging as you pull them apart, and you can see they stay charged. with the positive on the left and the negative on the right. And then the last one, the excess charge distributes evenly across the surface of the sphere. So both of them now are fully charged. If you bring an earth point to it, they will both discharge to the earth. So charge accumulation. Charge accumulates if charge generation exceeds charge relaxation or decay. This can occur in isolated metal plant, on personnel, with non-conducting materials such as plastics, etc., bulk liquids, especially when you've got insulating liquids, bulk powders, especially when you've got things like plastics, again, either fine powder or granules, and in mists or dust clouds. In these cases, the charge generation is building up faster than you can get rid of the charge, which means it's going to accumulate and get bigger and bigger and stronger. Here's a couple of examples for you for conductors. In A, we have a length of pipe with insulation between the pipes. So the middle section is isolated away from either side. This is an isolated conductor, and it will continue to charge and charge. And if an earth comes close to it or near it, then it will spark over to that. We've got B, we've got a metal drum. You would think that would be okay. But to keep the floor clean, what they've done is they put it on a pallet covered in plastic sheet. So now the drum has nowhere to go. The earth has to be continuous. In this case, it's not. So the material within the drum stays charged. Once you touch earth again, you get the spark. With C, you have an insulated drum with conducting material inside of it. Now you'd think conducting material, well, you won't accumulate charge, but it's flowing in at high rate into the drum, and it's got nowhere to go because the drum is insulating, so it remains charged. And when you go to pour it into the vessel, if it's a steel vessel, for instance, then it will spark. And then you've got someone with shoes on, insulating shoes. Again, the charge builds up on the person, like the car, and you end up sparking. In the other case, you've got metal isolated parts there, like donuts. They're isolated, not earthed, and again you get the same thing like A, but in reverse. And these build up the charge, and if there any earth nearby, then they will discharge to that earth. With insulators, they hold their charge and they can build it and keep it. So shrink wrap, for instance, going round, again, it won't lose its charge because it's an insulator. If you've got insulating powder coming off here on an LEV system, you've got a filter here with particles on the filters may be polypropylene and insulating again, so you get charge in there. And again, you're spraying inside the vessel and you've got powder which is insulating again. So we know we can generate charge, we know we can accumulate charge. Now, how does it get rid of itself? How do we get rid of that charge? Well, there's several ways of discharge that can occur. There's actually 6 of them. There's spark discharges, the most common, brush discharges, propagating brush discharges, corona, and cone. Corona is the least powerful of them, followed by brush, followed by either cone or spark, depending on the circumstances. And the big one is propagating brush, which can go up to a joule of energy. And also you've got lightning types, which are electrostatic discharges. So the effective and available energy depends on the source of the discharge. The most common one, as we see, is spark discharge, charged isolated conductors. The energy is calculated at half CV squared, so the voltage and the capacitance can be up to about 100 millijoules of energy, maybe a bit more in certain instances. So if you look at A, you've got an isolated metal drum and trolley. There's nylon wheels on the trolley. So you think you should be isolated, you should be okay, but the nylon wheels insulate the drum. You get near the metal pipe and it sparks. You got B, an isolated person, insulating footwear and or floor. And then you get the discharge as he goes to open the door. C is an isolated pipe section, what we spoke about before. And again, it's close to another pipe, which is earthed. And this can be caused by insulating gaskets and sleeve connections. And the last one we talked about is isolated conducting liquids in a insulating plastic drum. All types where you can get spark discharges. Brush discharges come off of insulators, and these can occur in many ways. If charges of one polarity are distributed on the surface of an insulator, brush discharges can occur as soon as the surface of an earthed electrode nears the surface of the insulator. Energy is fairly low, 3 to 4 millijoules. And you can see here, insulated plastic sacks. Brush discharges can occur from liquid surface or charged insulating liquids, from charged dust clouds, and from charged thunderclouds. Charged thunderclouds are outside really the remit of what we're talking about. This is when you take a nylon jumper off at night, you see those little sparks, they are brush discharges, 3 to 4 millijoules. Propagating brush discharges, the big ones, high charging situations on high resistivity material insulator with a metal substrate very close by. Energy can be greater than a joule of energy. So A, pneumatic conveying through coated metal duct or pipeline. If you're putting plastic pellets through a tube and you've got a bend, the pellets will smear around the bend and you run the risk of a propagating brush discharge. Internally coated cyclone, the same thing again, you've got a metal cyclone, you end up with thin deposits on the walls and you can run the risk of a propagating brush discharge. Insulating bulk container on an earth discharge chute. Again, you've got this metal substrate with the high energy plastic on it, and high speed conveyor belts. Again, you've got the metal there with thin deposits of insulator on it. The worst I've seen of this was acetate offcuts in a low IBC, and the man went to flatten them down because they were closed at the weekend and they couldn't collect till the Monday. So he pushed it down, went to push it down, and we had acetate sheets stuck to the side of the steel bulk container, and he got a propagating brush discharge. The whole of his arm went jet black and blue, and he was in hospital for 6 days and had basically a heart attack on the machine caused by it. Very powerful things. Corona discharges not really worried about these too much, but they're basically on sharp points. Corona is what you hear when you walk past pylons and you look up and you hear this hissing noise. That's often corona discharge. So they're insulator away from earth points, usually with a sharp point of edge, very low energies, 0.1 millijoules, can ignite very sensitive gases or gas oxygen mixtures. Not too worried about it in industry. Cone discharges. These discharges are observed in connection with charged and highly insulating bulk solids. Always happens in silos and bulk containers, normally not below 1 cubic meter. They're luminous like fingers of electricity firing out across the surface of the cone. Up to 25 millijoules for fine powder, but this is where things go differently, because if you've got granules, large granules, they can produce much bigger cone discharges. So if you have large insulating granules with fine powder above, this is a very dodgy situation to be in. They can ignite vapors, gases, and sensitive dusts. The one I got involved with this was a silo full of plastic pellets used for secondary windows, for double glazed windows. And they had an explosion one night, which blew the explosion vents. And on investigation, there was a Japanese engineer on site at the time who said there was a probe in there with a small piece of plastic on it. That plastic would have given a brush discharge to ignite the powder. Well, the powder had an MIE of 10 millijoules, so it wouldn't have been there. But the silo was full of insulating granules. And on further talking with the operators, one of the maintenance men said he looked through the observation window a few weeks prior and he saw a very pretty, glowing, radiated lightning going across the top of the bulk granules. And this was a cone discharge that caused the problem, and they ended up having to inert with nitrogen in the atmosphere. Lightning type discharges, I don't really want to get into this because you should have lightning conductors, etc., but it's between the cloud and the Earth's surface. Large clouds, very large clouds, compared to what happens in an industrial plant. So we've looked at some of these things. We've seen FIBCs, we've seen spraying into some sort of dryer there, spray gun. We've seen liquid through a tube, etc. So hazards from metal components, isolated conducting, fixed and mobile objects can store energy and be the source of spark discharges. So always make sure that your earth is continuous. So if you measure a length of pipeline, measure from one end to the other and make sure that you have a continuity to earth. If you detect something wrong, then measure it in stages where between flanges. And if you find an isolated conductor, then you need to bond it and have jumper leads probably on to the other plant. Energy can be in the range of 100 to 500 millijoules, and it can be compared directly to the worst case MIE of materials. So again, these things are called spark discharges, and they are the most common and they're the easiest to sort out on your plant. So when you do your electrical inspections, maybe get them to check the earth, including flying leads, such as what are used when you're filling propane tanks or filling forklift trucks from propane tanks. There are flying leads. Check the earth is working properly. Check that the pipeline is earthed properly. Check that any leads you use are earthed properly. This is your first line of defense. With personnel, the human body is a conductor basically, and you can have spark discharges. We've all got them. I don't know anyone who's never had an electrostatic discharge. You can walk, sharing, induction, you can get it all. If you want to know certain levels, then 0.1 millijoules undetectable by touch. It still ignites hydrogen and carbon disulfide in air and some hydrocarbons in oxygen. 0.25 millijoules, basically undetectable by us, but may ignite hydrocarbons and or gases in air. One millijoule, this is detectable like a feather brushing against your fingers and can ignite some sensitive dust clouds. 10 millijoule is a prickling sensation. You can ignite a lot of dust clouds. 100 millijoules, slight muscular contraction, very incentive. In 1 joule is very sharp muscular contractions, impotent incentivity. So charge generation of non-conductive solid materials. Tribocharging is the contact and separation with other surfaces, discrete or continuous. Charge sharing, contact with other charged bodies or materials, where you share the charge with them. We saw that with the balls, for instance. Ionic charging, but no charging by induction. You cannot charge an insulator by induction. So typical charging systems, movement of materials in plastic pipes, emptying or filling of sacks and bags, processing sheet or film, especially materials like acetates, for instance, sitting or walking on insulated surfaces. Hazards. They can isolate conductors. We get the spark. Can look at nozzles and lances, wire helices, gaskets, isolating bottom bins, for instance, flanges which can isolate the ball valve, backing flanges, etc. Can lead to ignition from brush discharges from non-conducting materials, which can ignite gases and vapors. But even though you may have an MIE of a dust of 1 millijoule, brush discharges cannot ignite them. This has now been proved. You could get up to propagating brush discharges with huge ignition energies. It can ignite gases, vapors in most dusts. Propagating brush charges can basically ignite anything that's flammable. So the hazards for powder charging. Obviously, charge is generated on powders during various operations, and some of the bad ones are conveying, milling and grinding, sieving, pouring, filling of emptying vessels, sacks, etc. If you want to know how a material is going to behave in these situations, then you'll need to look at the volume resistivity and charge relaxation time. It will give you some idea about whether you've got a conductor, something which is anti-static, or an insulator. With liquid charging, you've got pumping, you've got agitation, you've got filtration, and you've got mist formation. All these things can result in charging occurring. I've seen PTFE lined pipes with holes like bullet holes through them, which has been caused by electrostatic discharges. Again, highly insulating liquids and insulating powders moving through, causing massive electrostatic charge. Mists and dust clouds. Mists come from things like aerosols, and dust clouds can be highly charged, even with conducting materials. Mist can, don't forget that mists can ignite below the LEL of the liquid, so be very careful with mist. Not a lot is known about them. Charge levels depend on how the mist is generated, and they may induce charges on isolated conductors. So they may not be a risk in themselves, but you could generate charge onto an isolated conductor. So the summary. Firstly, establish that a flammable atmosphere is or could be present. What is the ignition sensitivity of the flammable atmosphere? In other words, its MIE. Do operational conditions affect the MIE, such as temperature or pressure, etc.? Is the material insulating or conducting? Where will maximum charging occur in the system? Obviously, where the most movement takes place and you have two phases going on, these would be some of the high charging areas. Can you estimate or measure the charging rate? What types of discharge are relevant? Are you storing in silos, in which case can cone discharge come into the equation? Or are you just looking at spark discharge or brush discharges? Do you have insulating plastics that could smear around a pipe and create propagating brush discharges? Can you calculate the maximum stored energy? Is action to prevent, reduce and control electrostatic hazards necessary? Do you have things in place to prevent or reduce it? Controlling measures, we have bonding, grounding, bonding and grounding. Note, check to ensure no isolated conductors can occur. What I'm telling you is you have to make sure that you're going to earth or the bond has got to be continuous. So avoid or minimize charge generation. Prevent charge accumulation if you can. Remove charge before hazardous potentials are reached. If avoidance of static charging and incentive discharges cannot be prevented, then flammable atmospheres must be avoided or controlled. You may end up having to use nitrogen under inert systems. So we looked at the bonding and grounding. Well, bonding is the act of connecting objects together, and basically you're making them at the same voltage. So the charge becomes equal on everything. So there's no risk of sparking between the objects. However, bonding does not remove the risk of static sparks entirely. If an object at a lower voltage, e.g. a grounded hose, comes into contact with the equipment, you could get a static spark discharge. So the best way of doing it is to ensure in the system you have grounding. This is connection to a suitable earth point with a suitable checked and verified electric cable. Earthing resistance to ground for metal-to-metal contact R should be less than 10 ohms. Also complies with lightning requirements. So this is the figure you should be looking at when you're measuring ground for earthing of all metal plant. So for pipelines, usually earth by connecting the plant together with flange bolts, vessels and structures. Bonding across joints are not necessary in many cases, but you may have sleeve couplings or aggressive atmospheres, corrosive type atmospheres like near the sea. Don't forget, if you've got painted pipework, then if you are going to use the bolts, use serrated washers so they cut through the paint and make contact. And again, When you've done these things, check it. Make sure you measure R less than 10 ohms. For movable equipment such as drums, trucks, feeders, drum pumps, any movable plant that you move into hazardous areas, earth is normally by contact with a suitable floor. But beware of insulating skids, feet, or wheels. This is a big mistake made by people. They forget to take that into consideration. Also, get your floors measured and checked to see they are static dissipative. Don't just assume they are because someone's told you they are. If the floor resistance is variable or uncertain, then you can use flying leads. This has got to be hardwired at one end, connected up before the operation starts, and break the connection only after the operation is complete. Here's a diagram here showing an earth proving unit, which if you're unloading a tanker, for instance, this is the type of system you would have in place. So with ground measures on a centrifuge, you see the braided hose, but also remember the pipework underneath. If it's metal pipework, also confirm that the metal pipework is earthed as well as the braided hose. For personnel, flying leads can be used to ground personnel, but people don't like walking around with these attached to them everywhere. They use them in the electronics industry quite a lot around their wrists, but it's not really practical in most manufacturing plants. It's more common to use static dissipative flooring and shoes, and the total resistance between the body and ground should be less than 100 megohms. Don't forget, if you're using static dissipative mats, these must be earthed. And check your floors, as I said before, to see if you can get away with using this method of earthing. These types of measures can reduce electrostatic ignition hazards. Use electrically grounded conductive plant. Increase liquid conductivity. If you can get additives to go in it. Try and control the flow velocity. Prevent free falling or splashing of liquids. Bottom fill if you can. Make sure you use full bore valves so you reduce the turbulence within the pipework. Control here, based on the properties and test results, if the electrostatic charge on the powder particles is sufficient to cause discharges from the surface of the bulk powder, you may have to use inert gas blanketing, or if you don't mind having explosions going off, you could use explosion relief panels. We'll have a quick look at FIBCs and their hazards. Basically, there's 4 types of FIBC. Type A, polypropylene insulating. Type B, a different type of polypropylene insulating. Type C, conducting threads, fully conducting. And type D, which is static dissipative in their design. So type A has no special features. The type of hazard you can get are basically everything. Do not use them in hazardous areas at all. Type B, you have a breakdown of less than 4 kV, so it reduces the energy of the discharge. You can still get brush, cone, and spark discharges. Use only for flammable powders, not gases, etc. Assess cone discharges, and these are types B, C, and D, and these cannot be earthed. For type C, resistivity of less than 10 to the 8 must be earthed in use. I've seen these bags in action without an earth on. These are a very dangerous way of working, and you get isolated conductor. Make sure they're earthed, and again, check to see the earth works. Type D are the most expensive, but also the best for anything. The type D FIBCs work if earthed or not. And often, especially in the pharmaceutical industry, they use liners. Again, the liners need to be checked. Can they go in combination with the FIBC to do the job of releasing the static charge buildup? So the selection here, bulk powder product, less than 0.1 millimeter. If we've got an MIE, which is massive, a joule, we can use non-explosive atmospheres, anything, explosive dust, B, C, and D, flammable gases and vapors in the surrounding atmospheres, C and D, only if the gas is a 2A or group 2B. So 1,000 millijoules down to 3 millijoules, non-explosive, we use B, C, and D, same as an explosive, and we've got the same arrangement for C and D for all the FBC selections for gases in 2A or 2B. Less than 3 millijoules, the first one now non-explosive and explosive, drop down to the use of C and D only. So the summary that we've come up with is the need for test data to understand if there is an electrostatic hazard. Test data can include the minimum ignition energy, minimum explosive concentration, power to volume resistivity, charge relaxation time, chargeability for powders. Minimum ignition energy, flash point, lower explosion limit conductivity for liquids. We've explained what electrostatics are all about, and you should have a bit of an understanding now about the way generation, accumulation, and discharge of them. We've shown you examples of incidents and types of equipment where electrostatic incidents can occur. We've looked at electrostatic hazard assessments and the things you need to consider, looked at charge generation and charge accumulation, considered the types of electrostatic discharge, and looked at electrostatic hazards on plants, considered grounding and earthing, particularly the earthing, and selection of FIBCs. I hope you found the webinar interesting and you learned something from it. And this is where I sign off now. Thank you for all attending the seminar.